section 15.4. So last time, this is an outcome of the chain rule, is being able to do implicit differentiation. And the implicit differentiation for 2D, when you have an implicit function of two variables, remember you get everything on the left and 0 on the right, then you're able to find the slope of the curve, you know, like the slope of the tangent line basically to the curve, and you use this handy formula. Negative big Fx over big Fy, where big F is defined as all the junk on one side, that stuff. So there's a similar analogous version in 3D, but again, step one, and if I don't see step one on your paper, prepare to die. Like, I don't go, I did it in my head. I want to see step one, and that is get everything on one side and 0 on the other, and you've got basically a general representation of a level surface where the constant is 0, so it's a surface, and this big F is a function of 3 variables. So that's going to be an implicit function of x and y. Now, why do you have that? Because a lot of surfaces don't pass the vertical line test. And you can't isolate the z on one side and everything else on the other. In other words, you can't write it explicitly and just get your regular partials, dz dx and dz dy explicitly. So the way that you'll get them, if you are given an implicit function of x and y, get everything on one side, 0 on the other, and then your dz dx is going to be negative big Fx over Fz, and your dz dy is going to be negative, don't forget the negative, big Fy over big Fz. Notice they both have the same denominators. So that's kind of helpful. But the thing that I want to make sure that you all have is when you watch my videos for partial derivatives, what is the geometric interpretation of, just say, dz dx? Does anybody remember what the geometric interpretation is when you get a dz dx? What does it mean? Like visually, what are you getting? Yeah, I get it's a partial, but what does anybody know?
Integrating a section across an axis.
I get that you're kind of on the right track.
Differentiating.
It's like this. It's like the cross-sectional view of two planes, and you can basically, it makes the slope.
Slope. You just said the word. Magic. Yes, it's a slope. So this is a slope, but the slope what?
In the positive x direction.
Very good. Very good. Excellent. So like if I have some surface, let's just have a capping surface like this, like some mountain, and you're standing up on the mountain, let's say this is you with your skis, okay? And you're looking in the positive x direction, the slope of the mountain in the positive x direction is going to be the partial of the function z with respect to x. On the other hand, if you wanted to ski in the positive y-axis direction, you would get the partial of z with respect to y, and that'll give you the slope going in the y-axis direction, okay? Today, we're going to do something very important as soon as I finish up with this section, is what if, you, as a skier, you're like, well, I don't want to ski in the positive x direction or the positive y direction. I want to ski, you know, like diagonally, like, you know, in the middle of the x and y axes. What's the slope going in that direction? That you're going to need a directional derivative for, and we're going to get to that today. Okay? So that was the point that I wanted to get, though, is that I wanted to make sure that you watched my videos and that you got, when you get a partial for a function of two variables, x and y, the dz dx gives you the slope of the surface in the positive x, and the dz dy gives you the slope in the positive y. That's important. If you can get that, it'll help you on some of the quiz stuff. So this surface right here, this is a surface, people, and it's not in the general representation format. And I challenge you to try to solve that for z and get z isolated on one side and everything else on the other, because it would be a challenge to get explicit form. I mean, you maybe could, but it would be really hard. So what if you did want to get the dz dx or the dz dy, those slopes? Because it still makes sense. So what I did for you is in my 3D grapher that I have, I graphed this surface for you. See up top here? 3x squared z plus 2z cubed minus 5 equals x squared y squared minus 3yz. Check out this surface. I can even change the color. Can you guys see that okay on your screens?
Yes.
Okay, I can
Perfectly.
change
Yeah.
the color, you know, ooh, what if I want red? Ooh, that's pretty. Purple. Ooh, okay. So you can see this is a surface. So if somebody's standing on that surface and they want to face in the positive x direction, what would be the slope that way versus the dz dy? What would be the slope of the surface going in the positive y-axis direction? Well, we can get it because we now have this cool formula that tells us how to get it. So what is the cool formula? Well, it's in that theorem. So we know, first let me do step one. So I need to get fxyz equals 0. This is step one, otherwise you can't even apply the theorem. And it doesn't matter which side of the equation you get everything on. You'll still end up with the same result. So I'm going to just move everything that isn't already on the left to the left. So I'll subtract x squared y squared from both sides, and I'll add 3yz to both sides, and now I have this general representation of the surface. So all the junk that's on the left-hand side, we're going to rename it big F xyz because it's a function of 3 variables. And so now we can get the partial of z with respect to x. This is the slope of the surface going in the positive x direction. It's going to be negative the partial of big F with respect to x divided by, oops, the big F partial with respect to z. That's what the theorem says. So let's go do this in slow motion. So I'm going to put the negative there so I don't forget. And then when I take the partial with respect to x, the first term, his partial will be 6xz. The second term's partial is 0 because there are no factors of x at all, and z is held constant. Minus 5, derivative is 0. Minus x squared y squared is going to give me minus 2x y squared. And then the plus 3yz, the derivative of that with respect to x is 0. And so we're done with the numerator. Now, the denominator, we're going to take the partial of big F with respect to z. So hold x's and y's constant. So the first term, 3x squared z, the derivative of that with respect to z is 3x squared. The next term, the derivative is 6z squared. And then the minus 5 and the minus x squared y squared, the derivative of that is 0 with respect to z because there's no z's in there. Those just look like pure numbers. And then the plus 3yz's derivative with respect to z is simply plus 3y. And we're done. So there's the dz dx. That would be the slope. And if you wanted to actually find the value of the slope, you know, get the ordered triple that lives on your surface. So you'd have to find a point, an ordered triple on this beautiful surface, which is currently purple, but I can change it to yellow. What the heck? You know, find your ordered triple. Say, let's say I want this point like right there. I want to know the slope, you know, in the positive x direction. And you would substitute the coordinates of that point into your slope, and you get the actual slope. And if it's a negative number, that means you're going downhill. That means if you did ski in that direction, you would be headed downhill. If you get a slope that's a positive number, woo, that means, well, you couldn't really ski because you'd be looking uphill. You'd have to instead climb up the hill if you get a positive slope. So please know the difference between that also. Okay. Now, what about the dz dy? Well, the theorem says negative partial of big F with respect to y divided by a partial of big F with respect to z. Now, we already know the denominator because it's the same denominator as the other partial. So we'll just copy that down, and then we're going to put the negative there in front so we don't forget him. And then taking the partial of this big old function here with respect to y. The first term, derivative of 3x squared z with respect to y is 0. The 2z cubed and a minus 5, that derivative is 0. Oh, the minus x squared y squared, well, we need to worry about that because that's going to give us minus 2x squared y, like that, and then plus, and then the derivative of 3yz with respect to y is 3z. And then you may want to, just to clean it up to make it look prettier, you can always distribute that negative, and then your dz dy will look a little nicer, and then you'll have, I'll just rewrite 2x squared minus 3z all over the 3x squared plus the 6z squared plus the 3y. Now, the last piece here, letter B, you want to find the slope of the graph in the x direction at the point -1, 0, 1. So which one of these partials would I use to find the slope of the graph of the equation in the x direction?
dz dx.
Good. So you're going to substitute the order triple negative 1, 0, 1. I'll let you do the substituting, and I'll just tell you that dz dx, and here's some notation for you. You put a vertical line here, and then the subscript notation at the bottom of the vertical line in very tiny font, you would put that order triple. And then after I did all the substituting, I got 2/3. Because this is positive, that means I'd be headed uphill if I were standing on the surface and I were looking in that direction. I certainly couldn't ski in that direction. And so we're officially done with section 15.4. Congratulations. Let's move on to directional derivatives and gradients. Okay. So I was reading an article while I cue this up that was talking about, is actually written for a computer science course as a professor from University of Washington who's been teaching there for like 30 years. And they did a study of students' grades versus the lectures that they attend, the lecture hours that they attend, you know, actual lectures that they go to and listen to. And surprise, 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 and I'm being sarcastic here, the students who, you know, attended lectures and, you know, went to the lectures or listened to the recording lectures, they're the ones who had the higher grades and higher scores. And the students who missed a lot of lecture or, you know, really weren't present for the lectures now that we're remote, those folks did not really do so well. Okay, so moral of story, you know the drill. Do yourself a favor and, you know, be in lecture and be present, be mindful. I mean, certainly logging in right now is great, but you wanna really hear what's going on. You know, if you don't like my lectures, you know, after going to them, you know, you can certainly look at the Zoom recordings, and I also highly encourage you to read the book. Okay, let's review. So the directional derivative is going to be really cool because it's going to give you a way to get the slope of your surface in any direction that you want, not just looking in the positive x direction or the positive y direction. So let's just do some review. Suppose you're standing on this surface here, which is a mountain, and it's represented by this function z equals fxy, and you want to get the slope of the hillside in the positive x-axis direction. What would you do to get it?
dz dx.
That's right. And then what if you wanted to get the slope in the positive y-axis direction?
dz dy.
So now you're going to learn to find the slope in any direction you please. Cool. And this is a new type of derivative, and it is called the directional derivative. Surprise, surprise. And that happens to be part of the title of today's lecture. Awesome. So this is exciting. I'm not going to have time to do the full derivation just because it's going to take me a while. But the idea is if you're standing on a curve somewhere, at, say at this point right here, this is you standing there, and you're like, hey, I want to get the slope, you know, facing this direction. So beneath you, you're going to have some straight line. And if you draw a curve that lives on the surface that passes through the point that you're standing on, and you draw a tangent line to that curve, what you really are going to say is that the slope of the surface is going to basically be the same as the slope of the tangent line to the curve. So this is where the whole derivation, the slope of the surface is equal to the slope of the tangent line to the curve that's on the surface that passes so it's in the direction of the straight line essentially, and at the point that you're standing on. So it's a lot going on, and just to sort of reiterate, if I were to do this whole proof, which I have done, and I got to skip it because I'm going to be hurting for time, is if you took a knife and you sliced through your point and through the surface, the intersection, basically, of the curve with the line is sort of where you're headed. So you're going to basically get a change of altitude over a change of distance down here. So you guys know that slope is equal to rise over run from your algebra course. The rise over run we're doing here is if I pick an arbitrary point on the curve, the rise would be the change in z, or delta z, all over your run, and the run would be this distance down here along the PQ line. So that would be your run. Okay, so I'm not going to do that, but if you did do all that, and your direction that you're looking at, the little direction vector is pointing, it's a unit vector, so its magnitude is 1, and the angle that it makes with the positive x-axis is known, you would then have your limit definition of the directional derivative. So I'm just going to write it all out so you have it, but it basically says, let u be a direction vector that's pointing you in the direction that you want to find your slope, which, you know, could be still in the x and y positive direction, but, you know, you probably want something different than that. If you have that in hand, then you can find your directional derivative in the direction of that unit vector. And here's the weird notation. Capital D, that stands for directional derivative, subscript u, that's saying in the direction of this unit vector, of the function that's representing your surface, okay? So if you want to find that, your du f of xy is going to be a limit as t goes to 0 of f evaluated x plus t cos theta, y plus t sine theta, oh boy, minus fxy. It's a difference quotient, just like all of these derivatives are, over t. And t is basically going to be the parameter that's involved to parameterize your line there in the xy plane. So if you guys know how to parameterize lines in the any 2D or 3D. So that's the parameter. And so as t goes to 0 down here in the xy plane, q gets really close to p, and then this point here gets really close to the point you're standing on. So it all squeezes down and you get your slope. We're not going to use this limit definition to get our directional derivatives, okay, thank God, mainly because it's pretty challenging. So it is a challenge to find the directional derivative using this limit definition. So instead we're going to do an easier way, and the working formula for finding directional derivatives in this class is going to be using this theorem here. This is one of them. There's going to be two if you pay attention today. I personally use the second one more than I use this first one. So full disclosure, this first theorem, to help you get the directional derivative, you're probably not going to use it very often, but it's a good introduction, okay? So we won't use this much. So please pay attention and write this down because the more common version is coming up. So it's a starter point though. Let f be a function of two variables, and let this little unit vector that's pointing you in the direction of where you want to find the slope, which is going to have a components cos theta sine theta, where theta is the angle it's making with the positive x-axis, then the directional derivative of f in the direction of u is denoted big D U F, and it's given by big D U F xy is you find the partial of your function with respect to x, and you multiply it with the first component of your unit vector. Plus, then you find the first partial of your function with respect to y, and you multiply that by the second component of your unit vector. Boom, and there it is. There's your directional derivative. Now, when you're standing on the mountain, let's go back to the picture. So there, let's say here you are, you know, let's say this is a point, this is where you're standing. You're like, hey, cool. And you want to find the slope, not pointing in the positive x and y axis direction. Let's say you want to find the slope looking this direction. So you basically, this vector here is a 2D vector. So you can like drop it down to the xy plane and then look here at this angle theta that it's making with the x-axis. And you're like, yeah, I want to know the slope going sort of diagonally in between the the X and Y axes. Okay, and the directional derivative is going to help you get that. But this little u, this direction vector, you can think of as if you, in your hand, here's your hand, you have a little compass, and the compass is maybe pointing you, and it's a 2D compass, so it's flat, is pointing you in the direction that you want to find your slope of. So that's sort of the plan. Oh, wait, the point that I wanted to make, I just lost sight. There's infinitely many different ways that you could turn your body. So here you are standing on the mountain. I hope you can appreciate that if you can turn your body in any direction and point yourself, you know, backwards, like back that way or this way or this way. There's infinity different directions you could turn your body. So there's going to be infinity directional derivatives at that point because there's infinity directions you could look. So that's the point I wanted to make. That's one of them. So there are infinitely many directional derivatives on the surface corresponding to a single point, one for any direction that you're pointing to. Now, let's ask some questions before we do some examples. Suppose the theta in this theorem were equal to 0. What does that mean? You know, so it means that here in the xy plane, you know, let's say here z, your little directional vector here, your u, is pointing in the same direction as the positive x-axis. So u is pointing in a positive x-axis direction. Okay, but if you use that theta in that formula, so it means that u, which is equal to cos theta sine theta, is really going to be cos 0 sine 0 if theta is equal to 0, and then that's going to have components 1 and 0. So your directional derivative for your function, if you use this theorem here, you're going to have fx times cos theta, but your cos theta is cos of 0, which is 1, plus your partial with respect to y times sine of theta, but if your theta is 0, sine of 0 is 0, and so your directional derivative pointing in the positive x-axis direction is that. Does that make sense to you?
Yes.
It should, because it's supposed to be fx when you're pointing in the positive x-axis direction. So I just want you to see this formula works. And similarly, if your theta is pi halves, what does that mean? Well, that means that your little direction vector, it's pointing you in the direction that you want to find your slope, then it would be 90 degrees essentially, because now you're looking 90 degrees from the x-axis. So then your little u would be cos of 90 degrees, sine of 90 degrees, but I believe cos of 90 is 0 and sine of 90 is 1. So then your directional derivative, if you're looking with the theta of pi halves or 90 degrees, would be fx, xy times your cosine theta, but your cosine theta is 0 plus your partial with respect to y times your sine of theta, but your sine of theta is 1, and then of course this term goes away and you're left with, oh, your slope in the 90 degree direction is fy, and that should make sense because you're exactly pointing in the direction of the positive y-axis. So I just did that. I want to prove to you the formula does work. So now let's do an example. And by the way, I'll never give you some example. Well, I could give you an example like this on a test, but it's just too easy. Too much information given to you for free. So let's take a look. They're giving you a surface described by that function fxy, 4 minus x squared minus 1/4 y squared. They want us to find the directional derivative of that guy at the point 1, 2 in this direction. And notice this is already a unit vector, which is a good thing, because it turns out if you're given a vector, a direction vector essentially, and it's not unitized, you're going to have to unitize it before you use it in this formula for directional derivative. If you fail to do that, your entire problem will be wrong, and I give you 0 points on quizzes and exams and the final. And yes, there's going to be a directional derivative problem on the final. And yes, if you don't unitize the vector to make it a unit vector first, you will get 0 points on that final exam question. I'm telling you in advance. This is one of the most important things you're learning this semester, so pay attention. Stay awake, people. Okay, So they're telling us cos pi thirds, sine pi thirds. So I claim that my unit vector, I could actually just figure out what his components are right now, because let's see, cosine of pi thirds, I think that's a half. And let's see, sine of pi thirds is square root of 3/2, right? So there it is. And then fx for this function, if you take the derivative of that with respect to x, is negative 2x. Fy is minus a fourth times the derivative of y squared with respect to y. And then let's reduce this to lowest terms, and we get negative a half y. So your directional derivative at any point xy would be given by, if you use this formula, fx times cos theta plus fy times sine theta is going to be negative 2x. For us, this is going to be the half for this particular unit vector. And then plus the fy, which we got negative a half y. And then we got, that is going to be square root of 3/2. Okay, and then they specifically said at the point 1, 2. So your directional derivative in the direction of a vector making pi thirds angle with the positive x-axis at the point 1, 2 is going to be, and I'm just going to substitute 1 in place of x in my formula right now, and I'll substitute 2 in place of y, and then rewrite this, and I'll get some really weird exact answer. Negative 1 minus square root of 3/2. And that is the slope in the direction of this unit vector. And I'm done. Now, they may ask you for an approximate answer, and this is negative 1.866 approximately. Okay, so there you have it. I'm done with example 1. Now, you have to be careful, and I'm being redundant here, but this is part of kind of the way I teach, is that the direction has to be a unit vector. If it is not a unit vector, it's your job to unitize it. And a lot of times they don't give you the hint, like unitize it. Sometimes my math lab is really nice and they do, but they may not. So you need to unitize it, which is also known as normalizing it. That's another way to say go unitize a vector, normalize it. Okay, so let's do an example now where it's more akin to what I'm going to be giving you. I'm not going to give you something this easy. So example 2, this is similar more to what I would do. So I go, oh, here's a lovely function. Go find his directional derivative at this point, and in this direction. Okay, now they're not giving us a unitized vector here. I hope you could see that this is not unitized. Well, how would you prove it? Well, go find its magnitude. And I think you'll find that this magnitude is definitely not a 1. So it's not unitized. So you got to go unitize it. And you all know how to unitize vectors now. I taught you that the first week of the semester. And this is one of the applications where you need to know how to unitize a vector, among many. One of them also is finding big T and big N, right? You need to know how to unitize a vector. So U is going to be the vector V all over its magnitude. So doing what we all know how to do here quickly. And so I'm going to get the vector 3, negative 4 divided by square root of 9 plus 6. Ooh, that's nice. That doesn't always happen. And it just turns out it's going to be square root of 25, which is 5. And then I'll have this. Now, folks, what I want you to get is that this 3/5 is somebody's it's a cosine of a theta. And this is a sine of theta. So in the formula above here, the cosine theta is simply the first component of your unitized direction vector. And the sine theta is the second component of your unitized direction vector. There's no need for you to go find theta. Like, don't waste valuable time going, ooh, now I better go get theta. Oh, gee. If I even catch you doing that, even if your answer is correct and my math lab gives you full credit, I'm going to take away points. Why? Because you didn't get this. This is like obvious. Don't waste valuable time, because it means you really don't get it. Okay? So this is the cosine, this is the sine. No need to actually find the theta. It's sort of already in the mix. So now let's go ahead and get the partials. And this is a pretty easy function to find partials of. So the derivative of x squared sine 2y with respect to x will be 2x times sine of 2y. And the partial with respect to y will be what? 2x squared cos of 2y. I think that looks right. And then, so your directional derivative, big D, subscript u, f, x, y, is going to look like the fx, 2x sine 2y, whatever that is, times the first component of that unitized direction vector, plus the fy, 2x squared cos 2y, times the second component of your unitized direction vector. And they want you to find the directional derivative at this point, 1 pi halves. No problem. We're just going to substitute the coordinates here, 1 pi halves, and you know the drill. Just start, plugging stuff in here. Sine of 2 times pi halves times 3/5 plus 2 times 1 squared cos of 2 times pi halves times negative 4/5. Now be careful here. This sign, after reducing, the argument is pi. So what's sine of pi?
0.
0. So this is gone because that's big fat 0. What about over here? After reducing the 2's there, you've got cosine pi, which is?
-1.
-1. Good. So you're going to have 2 times -1 times negative 4/5. Final answer is positive 8/5. And that's essentially the slope of your surface at the point, not the order triple, but below, downstairs in the xy plane, 1 pi halves, pointing in the direction of this vector 3, -4. And by the way, 3, -4 isn't that vector pointing down here in it looks like the vector is down there in quadrant 4 in the xy plane. Okay. All right, so you guys ready to try one?
Sure.
Yeah, you are, because I'm gonna put you into study groups, study buddy, and folks, listen up, because this is a lot of times when I take attendance, and if you're not around and I go into the study buddy breakout room and I'm calling your name and you're not helping your buddy, and by the way, I want you to work together, like talk to each other either via mic or whatever, and help each other out on this problem, because it's going to be a little bit hellacious. I'll just tell you that right now, because there's some work to be done. It's going to be multi steps, so get it done. All right, so please be here. This is part of the participation of you being in the live, not recorded classes. Okay, so here's, see, I've got 25 people in the room, drop it down to 24. How about if we do 12 rooms? That sounds good. Yeah. Okay, when I open up your room, you go in there. Bye. So I need to unitize my PQ, otherwise this won't work. So when I unitize the PQ vector, I'm going to have the square root of 2 squared plus 1 squared, that's square root of 5. So I'll get the vector with these components, -2 over square root of 5, -1 over square root of 5. And then I'm going to evaluate my partials at the point. Now, which point am I supposed to evaluate my partials at? The P or the Q, or does it matter?
P.
The P, because they said they want the directional derivative at the point P. So that's your job to evaluate your first partial of f with respect to x at the point 1, 0. And then when you plug in the point 1, 0, fx is 0. Oh man, that was easy. And then the other partial evaluated at the point 1, 0, after plugging stuff in, I get a negative x all over 1 plus 0. So I get -1. So your final answer, your directional derivative of f at the point 1, 0 is going to be fx times, the first component of your unit vector, but 0 times anything is 0, so forget that, plus -1, your fy, evaluated at the point, times the second component of your unitized direction vector. And then this, the negative times the negative is a positive, and you get your slope 1 over square root of 5. Okay? So there you go. So now we're going to do the second half of this section, and we're going to talk about gradients. And it's going to seem at first like, what does this have to do with directional derivatives? Man, this is really dumb. And the answer is going to come fairly quickly. So keep this in the back of your mind, this question. What do gradients have to do with directional derivatives? And why the heck are they discussing this weird thing called gradients right in the middle of the directional derivatives section? If you keep that in mind, I would claim the answer will come very soon. So we're going to do a new topic, gradients. So we've already discussed directional derivatives, and there's many directional derivatives at a point. You can turn in infinity directions, fine. So the question that might come to like a thinking student is like, in which direction should I move if I'm standing on the mountain where the function increases most rapidly? That would be, in other words, what's the direction I should face to have maximum slope? And that direction is called the direction of steepest ascent. That's a fancy way of saying, you know, going in the direction of the steepest slope, and is given by the gradient vector. So the gradient is a vector, and it's a very important vector because if you find the gradient at a point, it's going to point you in the direction of maximum slope. So it's really cool to know about gradients. Okay, fine. Here's the official definition of the gradient, and it also is going to tell you how to get it. So keep your eyes on this definition because it's going to save your rear end on many occasions. Okay, so you got a function of two variables, x and y. And by the way, you can always do the analogous gradient for functions of 3 or 4 or 5 variables at any time. And you want your first partials to exist. You'll see why in a minute. The gradient of f has this strange notation. It's an upside down triangle, which is actually a Greek letter. It's like a capital F, delta, upside down, F, X, Y. And so the way you're going to read this, by the way, anytime you see that, is don't read it as upside down triangle F of X, Y. You're going to read it as del, which is like short for delta, del F. Now, technically, I should put a big fat arrow on the top because this is a vector. But if you don't mind, if you'll forgive me for the rest of the semester, because gradients are known to be vectors, I'm going to drop the vector notation for my del F gradients, okay? Just because it's awkward. So del F, which is a vector, is going to be this cool vector. It's going to be a vector that simply has the partials of F as its components, and that's it. That's known as the gradient. Isn't that cool? Yeah, so what?
Yes, it's super cool.
It's super cool. So let's find a gradient, and then we'll use it for some stuff very soon. Okay. So let's find the gradient of z equals f of xy, which is given by y times ln x plus xy squared at the point 1, 2. Fine. So del f is your gradient. So it's going to be this vector. Okay, fine. Let's on the fly get these partials. Now that you know how to find partials, you should be experts. So what is the first partial of this function with respect to x? Well, let's do the first term. What's the derivative of y times ln of x with respect to x? So y is a constant, so y times, and then the derivative of ln x is?
1
X.
over x.
Mm-hmm. Okay, there's the first term, plus, and then what is the partial derivative of xy squared with respect to x?
y squared.
Y squared.
Okay, I'm done with the partial with respect to x. Now, comma, the other component of this gradient is going to be the other partial, the partial of this function with respect to y. So the derivative of y times ln x with respect to y is?
ln x.
Ln x.
Good. plus the derivative of xy squared with respect to y is?
2xy.
Mhm.
2xy.
Okay, got that guy, and we've got the gradient. And this gives us, we can find the gradient at any point as long as we know the coordinates x and y. So they want us to evaluate it specifically at the point 1, 2, and I'm just doing all the notation here, del f at 1, 2. And you know the drill, you're just going to do some substitution everywhere. And my Microsoft is starting to run slow again. Okay, ln of 1 is a nice number. It's called 0. And then doing some of the arithmetic here, I have 2 plus 4. That's 6 for the first component and 4 for the second. And I'm done. And there's my gradient. Cool. All right. Quick checkpoint questions. Question number 1. Is the directional derivative a vector or a scalar? So we spent the first half of today's lecture doing all sorts of fun and play with directional derivatives. Is the directional derivative a vector or a scalar?
Scalar.
Taylor.
Scalar.
Scalar.
Very good. Know that. So often on like midterms and finals, I ask a student for a directional derivative and they give me a freaking vector. I'm like, what? I don't even give them partial credit. I don't care what they did. I just take away all their points. It's like, you missed the boat, buddy. It's a scalar. It gives you a slope. Now, is the gradient a vector or a scalar?
A vector.
It's
A vector.
vector. So know the difference. Okay. Now, because the gradient of f is a vector, it turns out that we can write the directional derivative of f at a unit vector u as a dot product. Well, why? So I want you to go back to the original definition that I gave you for directional derivatives, and I did tell you that we won't use this much, and now you're going to find out why, because you kind of, it's sort of in the mix. Do you notice that this directional derivative theorem has something times something plus something times something else? Doesn't that remind you of the flavor of a dot product?
Yeah.
It does, because it is a dot product. Really? Yeah, but I didn't want to tell you when I was giving it to you back then because it would have freaked you out. But now you're ready. It really is a dot product. So this new definition for directional derivative that we're about to write down isn't really a new directional derivative theorem, okay? It's the same thing as the original, but now we're just showing you that who is it the dot product of. So you still need a unitized direction vector pointing you in the direction that you want to get your directional derivative, because, oh boy, that did not go so well, sorry. Because you're going to take the dot product of that guy with who? Who do you think you're taking the dot
Gradient.
product? Yes, you're taking the gradient of your function, which is a vector. We just found that out. And you're going to dot product that with your unitized direction vector. And that is the directional derivative, folks. Cool, huh? So knowing that, let's...
That is pretty cool, actually.
I know, this, I'm telling you, this is way cool. I mean, if you're not duly impressed right now, you're not doing this class right. Like, that is amazing that you can get a slope of a surface at a point by taking the dot product of the direction that you're facing with the gradient. It's just awesome. Okay, let's use the gradient and help us get a directional derivative now, and then we'll do some cool properties of the gradient, okay? So besides being able to use a gradient to get a directional derivative, there's other things that the gradient is really awesome for. We'll see in a moment when we hit this theorem. But let's do this example 5 first. Okay, fine. We want to find the gradient of this function, 3x squared minus 2y squared, and we're going to use that gradient to find the directional derivative. At this point, well, we can call this point P, in the direction from this point P to this other point, we're going to call Q. So I hope you can appreciate now, after doing one of these problems, this is going to be a multi-step problem. So first up, I'm going to go get my partials real fast. The partial with respect to x is simply 6x. Nice. The partial with respect to y is simply negative 4y. Great. So del f, that's my gradient, which is simply a vector that contains the partials as its components, is simply going to be this cool vector, 6x negative 4y. Nice. Now, the gradient evaluated at the point P, this is some notation that Dr. Vallone used to use, which if I do in the special, textbook notation, I'm just going to substitute the point P, which has coordinates negative 3/4 and 0. So I'm going to get this vector. Oh boy, I get what? Negative 18/4, 0. And of course, I always like you to reduce, although my math lab doesn't always ask you to reduce, but I dock you a point every time you fail to reduce. So there's your gradient at the point P. Fine. Now we need to get our vector that is our direction vector for the directional derivative. So I'm going to form the vector PQ. Remember, terminal minus initial. Terminal minus initial. This is important. Order matters. And so I'll get a negative 3/4, which is really a positive 3/4. And the other component is 1. And don't forget to unitize it. Unitize it. So that unit vector is going to be the PQ vector divided by the magnitude of the PQ. Oh my goodness. And this is going to be kind of a pain in the rear end because, oh, fractions. Oh boy, yeah. Oh, good Lord. Okay, 3/4 squared is 9/16, right? Yeah. And, you can clean that up. If I do this in super slow motion, which is kind of how I like you guys to do it when you're showing me your handwritten work, you can turn 1 into a fraction that has a 16 as its denominator. And then the beauty of that is now your radicand looks like the quotient 25/16. But then if you are taking a square root of a quotient, you're allowed to use the law of radicals that says, hey, rewrite it as a quotient of radicals. And then this is simply 5/4, but dividing by 5/4 is the same as multiplying by the reciprocal, which is 4/5. And then using my knowledge of scalar multiplication and reducing, I get my direction vector to be the vector 3/5, 4/5. And now I can finish the problem. My directional derivative of f at the point P is going to be the dot product of the gradient with the unit vector. So for me, that's going to be the vector negative 9/2, 0, dot product with the vector 3/5, 4/5. And you guys know how to find the dot product. You're going to take the product of the x components and then add that to, well, 0 times anything is 0. And then what the heck is negative 9/2 times 3/5? I get negative 27/10. Woohoo! And I'm done. So I just used the gradient to help me go get a directional derivative. Fine. And we're done with that problem. Okay. So why is the gradient cool besides it can help you get a directional derivative? There's more. Here's why it's cool. So here's some properties of the gradient. If your gradient is the 0 vector, which can happen, okay, then it's going to be that the directional derivative is always going to be 0. Your slope's basically going to be 0 for any direction that you care to look at. And this should be obvious, I hope, because anytime you take the dot product with a 0 vector, you're going to get a 0 as an answer. Okay, fine. Now, these aren't so obvious. So these are the cool properties of the gradient and why you care, especially if you're a physics person. Like physics folks really care about the gradient. Because a lot of times when they're talking about heat transfer, like if you have a hot or heated up, say, pipe, it's going to cool off. And, it's going to cool off down the gradient. A lot of times they'll tell you this. Okay? So the direction of maximum increase, that steepest descent, that steepest slope, is given by the direction of your gradient. That's going to be like a pointer pointing in the direction of the steepest slope. Now the actual maximum value, the maximum slope itself, the scalar, if you will, is going to be the magnitude of that gradient. And that is like awesome. Now, Similarly, the direction of minimum decrease, the steepest descent, so that's if you were standing on a mountain and you wanted to ski down the mountain, you would simply ski in the opposite direction of the gradient if you were a hot dogger skier and you like super steep slopes. Just ski in the opposite direction of the gradient to get the most negative slope. And then the minimum value, or what is that slope, it's going to be negative the magnitude of the gradient. So that's the actual value of the slope. That's awesome. Here's a quick proof of this. So part one, I hope, like, number one is like the obvious, but I'll just say it. You know, if your gradient del F is equal to a zero vector, then for any direction that you want to care to find your directional derivative, the directional derivative is going to be del F dot product with u, but that's going to be the zero vector dotted with u, which is going to be 0. Okay, so that's like, all right, fine. Now, so for numbers 2 and 3, here's the proof. If your del F is not the zero vector, so it's, in other words, it's a little more interesting, then let theta be an angle between del F and the unit vector u. That's the direction that you're trying to find your directional derivative for. Now, what you guys should remember from the first week of class, the angle between two vectors can be found. Why? Because you guys know that the cosine of the angle is, you know, like so. So I'm not going to find it, but let's go ahead and do this. If the directional derivative is defined as the dot product of those two vectors from that theorem that I taught you in the first week of class, that is exactly the same as cosine of the angle between them multiplied by the product of their magnitudes. Do you guys remember this theorem at all?
Yes.
I hope so.
Yes.
Now, because u is a unit vector, what is the magnitude of u? This is not a trick question. Yeah. So really, the directional derivative is always going to be this. It's always going to be cosine theta. So this is an alternate way to find your directional derivative, multiplied by the magnitude of your gradient. But now let's think about that. What are all the possibilities of this number? Because directional derivatives are scalars. What are all the possibilities of cosine? Well, let's talk about the maximum. What's the maximum that cosine can ever reach, knowing what you know about the cosine graph?
1.
1. So
One.
the max of a directional derivative will be when cosine theta is at a max, which is when cosine theta is equal to a 1. Yes? Does everybody buy this? So what do you know when cosine theta is equal to a 1? What's the angle? You know, if you took arc cos of both sides, what is cos inverse of 1? Quick, come on.
0.
0. So what we're saying is that you can maximize your directional derivative if the angle between your gradient and your unit vector is 0 degrees. What does that mean? That means you're pointing in the direction of the gradient. So that's how you maximize, you know, it's the same direction as your gradient. You're pointing in the same direction as your gradient. That's why it's going to give you a max. And then similarly, when is cosine the minimum? So cosine theta equals -1 is going to give you a min. And what is your theta when your cosine is the least it could possibly be?
Pi.
Pi.
Which is 180 degrees. So if you want to go in the direction of the least slope, or the steepest descent, go in the opposite direction of your gradient, and that's going to give you the min. So there, I'm done with the proof. So to visualize these properties of the gradient, imagine a skier coming down a mountain, and if you are given the mountain's function, z equals fxy, and that gives you the altitude, then the vector negative the gradient indicates the compass direction of steepest descent. You know, you go in the opposite direction of the gradient, you'll be going downhill. Okay, now let's do a really nice modeling of all of this. We're running short on time, but I think this will probably be enough for you to do your quiz by Sunday. So another way to think about functions of two variables, instead of thinking about mountains and surfaces, I want you to think in a totally different way now. So I'm going to ask you to like imagine something. Imagine instead of a surface and graphing the surface of this, that this is a temperature function. So at any point xy, so this is your xy plane, the value that you get when you plug in a point into this function is the temperature at that point, T. So like you could find the temperature, say at the point 0, 0, if you plug in 0, 0 here, it'll give you 20, degrees or whatever. And so you're getting a temperature instead of an altitude. That's cool. And so thinking along those lines, suppose there was an ant walking on this hot metal plate. So this is going to be a hot metal plate or a hot stove. And we're overlaying a rectangular coordinate system on top of our hot stove. And this function represents the temperature at any point on that metal plate. So let's say the ant is located at the point 2, -3. So he's down here. Which direction should the ant move if he wants to increase his temperature the most rapidly? So let's say this is a heat-seeking ant. Which direction should he go? Well, I claim he should go in the direction of the gradient. So let's go get the gradient. Okay, that's simply going to be a vector that contains the partials. And if I do the partial of this big T function with respect to x, I get -8x. And if I do the partial of big T with respect to y, I get that. And then the maximum increase direction is going to be simply del T evaluated right where the ant is at the point 2, -3. So I'm simply going to substitute the coordinates of this point where the ant is sitting. I'm sure the ant is getting burned up by now, but -16, +6. Now, if you graph this vector in standard position, remember, standard position is where the origin is the initial point. You would first graph the point -16, 6, like way out here, and then you would draw a vector, woo, going over there. So this is the vector -16, 6. I'm going to lift it up and I'm not doing a very good job. It actually should point a little bit more up, not draw on the scale. I claim that that vector, if I drew it on this hot metal plate, is telling the ant to go into this direction in order to heat himself up. Because let's say he's cold and he wants to get hotter. Go in that direction, ant, okay? And you'll get hotter, okay? Now, what's the actual rate of this max increase? So if the ant starts walking along that vector, at what rate is he increasing his temperature? And it turns out that rate is going to be the magnitude. That's the value of the gradient at the, and so this is going to be square root of, oh, good God, 292, I think. And that's approximately, I'm going to get approximately 17.09 degrees. We'll say it's in degrees Celsius here because they told us. And per centimeter, because we're doing, they said X and Y are measured in centimeters. So that's pretty fast increase. The ant starts walking along that vector and he's like, whoa, I'm getting hot pretty quick. But here's the problem, though. You have to be careful. The minute the ant moves away from his current situation of the point 2, -3, like the minute he steps off and starts increasing his temperature, the gradient does change. So you would want to continually, when you have a GPS system and you're constantly getting monitored, he'd have to kind of change his direction the minute he starts walking. And every time he moves a little bit, recalculating his gradient in the direction. It turns out the path he would take would eventually kind of be a curve here. It would take him to the center because the center for this hot metal plate is the hottest place on the whole metal plate. But let's talk about level curves. So what are the level curves for this function? This is review for the quiz you just took the other day. So remember, when you're finding level curves, you set your function equal to a constant. That's the way you find what your level curves look like. And if I rearrange this equation and kind of make it look prettier by keeping the x squared, y squared terms on one side and moving the constant to the other, I claim that the level curves will look like ellipses. Okay, so what does that mean? If I did graph some of these ellipses, I would get like, and I'm not going to graph every single one of them, but I'll just do this quickly. You would get ellipses that would sort of be, would have a longer major axis in a vertical y direction. So if the ant stayed on his own level, personal level curve right there, let's say he didn't want to get hotter. Let's say the ant was like, hey, I'm good. I like this temperature. Where else can I go but stay at the same temperature? As long as he stayed on this ellipse that he's on, he'll stay at his same temperature and not change, okay? So that's kind of important to know. Which level curve is that ant currently on? Well, if you plug the point 2, -3 into this equation, you would find the k that he would be on, and I think his k is like -5, and he's on a certain ellipse. Okay, now what? The other thing I want you to notice that's super important to this picture, can you see that this level curve that the ant is on that I drew here, that ellipse, is orthogonal to the gradient? That's always going to be the case, that your gradient is always going to be orthogonal to your level curves. That's a big wow. So if the ant wants to stay at the same temperature, he should stay on that level curve. So what does that mean? If you did have some vector valued function describing that curve, and you guys, you know how to parameterize, we could do that, and you looked at the tangent vector to the curve right there, call it r prime. I claim that r prime would be orthogonal to your gradient. So so if you had a tangent vector, I'm calling it r prime, but they're calling it u, the rate of change in that direction would be 0 because you'd be staying the same because it's tangent to your level curve. So your gradient, if you dot product it with r prime, or u, that what I'm kind of calling it u right now, you'll get 0. And that's very amazing. So the theorem that the gradient is normal to level curves is really important. Just put a star by it because you're gonna need to know that. And so I'll finish up today with doing functions of 3 variables. Okay, functions of 3 variables, you can't really graph a function of 3 variables because you would need 4 dimensions, but we certainly can talk about it and talk about it very intelligently. For example, this next example, look at this function. It's a function of 3 variables. Well, sure, I can't graph it. It's not going to like be a surface or a curve. But suppose that in 3D, let's say at any point, x, y, z, this function represents a temperature, just say. So let's say you're in a room, I'm in my office here, and if I overlaid a 3-dimensional rectangular coordinate system on top of my room and said, hey, the origin is that corner over there, and then graphed it all out, I could have this function represent the temperature anywhere in 3D in my office. Fine. So we could talk about temperature being represented by this. So find the gradient of this function of 3 variables at this point. So a function of 3 variables gradient, and you can just, this is analogous to function of 2 variables, it's just going to be a vector that has all the first partials as its components. That's all. So easy peasy, let's go get the gradient for this function of 3 variables. Fine. It'll be 2x, 2y, and then fc is going to be -4. Okay? And if they want it at that point, no problem. The gradient del f at 2, 1, -1 will be, and you're just going to do some substituting, 2 for x, 1 for y, and -1 for z, but there are no z's in this particular guy. So this 4, 2, -4 is my gradient. Okay, fine. Now, folks, what is the significance of this? If I'm at a point, like let's say I'm right where my nose is. Let's say that's the point x, y, z. Okay, I got my nose. let's say I'm in this, I got this temperature function. If there was a bug on my nose, which direction should the bug travel if the bug would like to get warmer? Get even warmer than he is sitting on the edge of my nose. He'd go in the direction of this gradient. And that would get him to start increasing his temperature maximum. Okay, let's find a directional derivative of f at this point. Fine. In the direction of this vector. Well, step one is unitize it. And if you don't, you'll get 0 points. So when you unitize your direction vector here first, what the heck is that? I think that's square root of 49. Ooh, nice, which is 7. Cool. So my unitized vector is going to be -6/7, 3/7, and -2/7. That'll be the components, fine. And then the directional derivative of the function at the point 2, 1, -1 is going to be the dot product of the gradient with my direction vector. Cool. And I already got my gradient from part A. And take the dot product of that with my unitized direction vector, -6/7, 3/7, that's a 3, -2/7, and that's going to end up being -24/7 plus 6/7 plus 8/7, and that's going to give me -10/7. Okay? So what's the direction of maximum increase for the function at the point 2, 1, -1? And notice it's a direction, which means the answer is going to be a vector. So I'm going to open it up. Are you guys awake?
That's the gradient. Yeah.
That is the gradient. Exactly. So go in the direction of the gradient. Go in direction of gradient. And so that would be, the answer is part A. So go in the direction of del F 2, 1, -1, which we got already, which is this direction, 4, 2, -4, that vector with those components. Boom, there you go. Go in that direction. Okay, now what is the maximum rate of change for the function at the point 2, 1, -1?
The magnitude of del F.
The magnitude of the gradient at that point. Fine. So go get the magnitude of the gradient. And, oh man, what's 16 plus 4 plus 16? Oh, nice, square root of 36. I don't always get that lucky. All right, 6. And then describe the level surfaces for the function. So step 1 is set the function equal to some constant, I'll just call it k, and then examine that equation and see if it reminds you of any surface type equation that you ran into from the past. And here we have x squared and y squared are positive, and if you move z to the other side, you end up with paraboloids. So the level surfaces are paraboloids. So in my office here, if this were the space I was talking about, this is a temperature function, I'd have a whole collection of paraboloids, and so my nose intersects one of these paraboloids. Woo! And if that bug were on my nose and wanted to keep the same temperature and not get colder or hotter, as long as he stayed on that level surface paraboloid and never left that paraboloid, he would get to stay at his same temperature. But the minute he moved off of that paraboloid, his temperature will change. And if he wants to go in the direction where he get the hottest the quickest, he should go in the direction of the gradient. Okay, so that's directional derivatives. And all I'm going to say is that del F, even though it does give you the directional derivative slope on a 3D surface, it is a 2D vector. And 3D gradients are different, so please know the difference. This is a 2D vector and it's in the XY plane. This is in space. Okay, so it's a different vector. So you may want to read this a little bit, and they're just reiterating that gradients are always orthogonal to level curves. And the final big theorem is that gradients that have 3 variable gradients are normal, aka orthogonal, to level surfaces. And this is a biggie because we're going to use this in the next section. 15.6, sorry. I think we're in 15.5 right now. Okay, I'm done. I'll stay after about 5 minutes or so till I get ready for my next class. I have office hours today at noon. You're welcome to come. Noon till 2. If I don't see you, I'll see you Monday. Please do well on quiz 5. It's worth 200 points. I'm jacking up the points double just to entice you to take it because it's intense. Good luck. Bye.
See you in office hours, Professor.
Okay, I'll look forward to it.
Bye. Thank you.
Yeah.
Can you scroll to like page 12
I
or
sure
page
can.
5, please?